Okay, so for the final talk today, it's a pleasure to welcome Alisa Knizel, who's going to talk on stationary measure for the open KPZ equation.
Good afternoon. Thank you very much for the invitation to an opportunity to speak here. It's a pleasure. So I will talk about my joint work with Ivan Corwin about the construction of the stationary measure and for the KPZ equation. And I will start with some background on the KPZ equation and the KPZ universality class. So the KPZ equation models the stochastic growth of interfaces. So let us compare the following two mechanisms which are presented on this slide. So the following two models. On the left, we see the model which is called the random deposition model, which is one of the simplest and least realistic models for randomly growing one-dimensional interface. So here the dynamics is the following: the unit blocks are falling independently in parallel from the sky above each side of lattice Z, which are like these locations of the unit cubes which you see in the bottom, and the falling of the cubes occurs according to in time according to exponential distribution. So this is the model. This is a Markov process, and it's quite simple to analyze since each column grows independently. So like overall, we see the linear growth of the towers of blocks, and the fluctuations of the height of the towers in this model, according to the central limit theorem, will be of order square root of t, where t is time. So this is the first model. And now the model on the right. So the model on the right is called the ballistic deposition model. So it was introduced in 1959 by Volt. And it's supposed to be a much more realistic model. So another name of it is also the sticky block model. As before, blocks fall accordingly to IAD exponential weighting times. However, now a block will stick to the first edge against which it becomes incident. So this is the sticky mechanism that you see here. So the yellow unit block sticks to the first side of other block that it meets or meets during the fall. So it turns out that this stickiness actually radically changes the behavior of this growth process. So if we now look at the simulations, so here, in the bottom, we see the pictures with the simulations of the interface profile for these two models. We'll see that the height profile is very rough on the left, and it's kind of like much smoother on the right and has this like nice pattern, like some smaller like empty and also like on the left here, well, this like white and gray colors, they're just for the convenience of the viewer. They do not represent like anything in specific. So on the left we don't have any holes like while the interface is growing, and on the right we have like these sporadic regions like where like no blocks are present, occurring like sporadically here. So we see that the like overall behavior seems to be quite different, and it's indeed at least according to the simulations is supposed to be the case. So like the model, the ballistic deposition model is well, still not analyzed rigorously. So it's known that like overall, due to the work of Sepalainen, it's known that overall the growth rate of the height of the interface is still linear. However, we don't know exactly what are the fluctuations. So they're conjectured to be of the order t to the 1/3 for the model on the right, this ballistic deposition model. And famously, it's like this model, the ballistic deposition model is supposed to be governed by the following growth mechanism, which is represented by the KPZ equation, Kardar-Parisi-Zhang equation, which has the following form. So here H is the height of the interface, so it depends on time and the space variable x. So now they are the continuous variables. And on the right, we see like the sum of the three mechanisms of growth of this interface, which we discussed. So starting from the right, Xi here is the space-time white noise, which can be like understood in terms of this growth process as this mechanism which kicks, which gives this like kick at different places of the interface to grow like by one, which corresponds to this independent like fall of the independent arrival of unit cubes at different locations along the space direction. So this is the first mechanism. Then the middle term here is the relaxation mechanism. So like this sort of like the mechanism which gathers all the interface together. And like we don't see like a very, like if we go back to the simulation, we don't see a very like a sharp and deep holes in the interface. So like it's yeah, it's sort of like much more smooth. And the most important mechanism is the is given by this first term, the nonlinear term, where we yeah, so where we see the mechanism of the sticking, so the lateral growth. So the interface doesn't grow just up linearly; it also grows to the side. So this this quadratic term here, which sorry, it's the second term. The quadratic term here, which represents this lateral growth, and this is the stochastic PD, which is called the KPZ equation. So the KPZ equation can be analyzed for many different initial conditions. So the KPZ equation on the whole line. So like or like for example with periodic boundary conditions, the initial condition that we'll be interested in is the so-called open KPZ, when we'll be restricting our attention to a certain interval of space. Okay, so yeah, so this KPZ equation, it lies at the center of the so-called KPZ universality class, the class of models which conjecturally share like the same asymptotic properties for the fluctuations and are like similar in their mechanism of growth to the ballistic aggregation to this ballistic deposition model. And if we talk about some examples from the real life, the models under like certain conditions, the following models as the growth of the interface of the snowflakes on the wind shell, or the spread of the front line of the fire, like when you have the fire, when you have the grass field on fire, or like the spill of the drop of the coffee on the table, like the growth of interfaces of all these real life processes. They are supposed, under certain conditions, they're also supposed to be of the same flavor, and they're supposed to also belong to this KPZ universality class. So one of the natural questions about it is to understand, in particular, the steady state of this KPZ equation, which is supposed to model this the growth of the height function. And for the case of the whole line and the periodic boundary condition, this type of question was understood. However, and I will talk in more detail about that. However, the question about the steady state for the open KPZ remained open until recently. So, okay, so now I will need to say a couple of more words about the notations for the open KPZ, the equation on an interval. So we'll consider the interval from 0 to 1, and we will parameterize the boundary parameters with u and v, which are real numbers, and we'll set the following conditions: that the derivative on the left is equal to at the left edge is equal to u, and the derivative at the right edge is equal to minus v. So this is the inhomogeneous Neumann boundary conditions that we consider for the open KPZ equation. So now the question about the solution to the KPZ equation, the notion of the solution, proved to be a notoriously hard question. So I will not go into very much detail about how to rigorously define the solution. So the approach that I will take for the talk is through the connection between the KPZ equation and the stochastic heat equation. So I will talk about the notion of the solution for the KPZ equation, which is called the Hopf-Kohl solution. So now if we consider the stochastic heat equation, which is written here, with the following boundary conditions. Also, these derivatives are written in terms of the parameters u and v. Then formally, so it's much easier to formally make sense of the solution for the stochastic heat equation. And now, if we take the logarithm of the solution, this function z, then it formally solves the open KPZ equation. So when I will talk about the solution here, I will talk in terms of this this connection with the stochastic heat equation. Okay, so this is the notion of the solution for the KPZ equation. And now the type of the solution that I'm interested in is the stationary one. So the one which has the following property. So the stationary solution, the stationary measure for the open KPZ equation is the law on the random data. So in our case, it will be labeled by the initial conditions, which are these parameters u and v. And the stationarity is the property that this difference of between the function h at time t and space location x minus h at time t and 0 as a process in x is independent of time. So this is the stationarity property. And as I mentioned, in the case of the KPZ on the full line, it was known in the physics literature for quite some time, and then rigorously shown by Fanoki and Castell that the stationary measure is Brownian. on the full line, and it's also Brownian, so it's Brownian motion and Brownian breach in the case of periodic boundary condition, which was shown by Har and Mattingly recently in 2018. So this is the these were like the two cases which were known rigorously, and why the question about the open KPZ. So the expectation was, like, even in the physics literature, the answer was not predicted. And the expectation was that for a general case of parameters U and V, the stationary measure will not be Brownian anymore. So the expectation was that the answer would be more complicated, which indeed turned out to be the case, which follows from our work. So this is the background which I wanted to start with on the problem. So next, I will explain what is the starting point of our investigation. So how one can try to understand this stationary measure. And the answer comes from the connection between the KPZ equation and a certain discrete model, which also lies in this KPZ universality class. So the discrete model is the following. It's called the asymmetric simple exclusion process. And in our case, we'll consider, so it also can be viewed with different boundary conditions. So the one that we consider, which is related to the open KPZ, is called open ASAP. And it's the Markov process on the configurations of particles on the line. So the particles in this picture are the red dots. So they can be located at any at the integer sides from and the sides are labeled from 1 to capital N. So N is equal to 10 in this picture. So yeah, so we fix this interval from 1 to N, and particles, only one particle, at most one particle can occupy the side. So this is our configuration space, and the dynamics on the model is the following. So it depends on 5 parameters: alpha, beta, gamma, delta, and Q. And the dynamics is organized as follows. So we have 2 reservoirs, which are pictured by these gray cubes in this figure. Yeah, so there's a reservoir on the left and the reservoir on the right. So the particles can jump into the system and out of the system. So this interval is connected to these reservoirs. So the particle can jump only by 1 to the left or right, and only if the nearby site is unoccupied. And all these parameters, they represent the rate. So with the rate with which the particle is jumping, and all the moves are done according to, again, exponential clocks, which are independent of each other. So this is the description of the dynamics for this system, for the open ASAP. And yeah, so this is so this is the well, you can think about it as one of the simplest traffic models. So if we think about these particles as cars, and they are moving along this and this interval is this particular segment of the road. Yeah, so this is the description of the model in terms of the particle configuration. In order to relate it to the pictures which we've seen before, we'll consider the following observable of the system, which is called the height function. And it will, in the language of the height function, this model will be can be viewed as a so-called Kohn-Grove model. So the idea is that yeah, so this So I'm talking now about the zigzag profile, which you see on this picture on top of the configuration of particles. So to every configuration of particles on the interval, we relate the following zigzag line, which we view as a height function of the system. So the correspondence is the following. So I will explain like what is the initial condition on the next slide. So we start at some point on the left, and then the zigzag path is drawn in the following way. So it either goes up by 1 or down by 1, depending on whether so it is constructed like from the from just like unit segments, and the segment is going up if it sees like the particle when we project the vertex downstairs, and it goes down in the case there's no particle. So we see here that first there's a particle, the red particle at location 1, so the profile goes up, then goes down, there is no particle, then goes up by 2, there are 2 particles, and so forth. So this is like the way how the height profile is constructed, and this is the and in terms of this zigzag path, the dynamics of the system is now organized as following, with either so if we look in the middle of this profile, we see this picture where like once the particle is jumping to the left, is the same as moving this unit triangle, which is downwards to the upward position. This is what happens when the particle is moving to the left, and when the particle is moving to the right, we are doing the vice versa procedure. So the triangle, the unit triangle, which is upwards, now becomes downwards with raise 1 and q accordingly. So this is the dynamics on the height profile. So in this setup with the height function, we now see like the clear connection with the previous setup of the interface growth models that we discussed. Okay, so formally, this height function can be defined in the following way. So for t, the time variable greater than 0, and the location, so we also include here the location 0 from 0 to n, we define it in the following way. So this summation of variables tau it are the so-called occupancy variables. They are equal to 0 or 1, depending on whether we see the particle or the particle is not present. And the initial condition that we impose here is minus twice the net current of particles at time t, which is equal to the number of particles to enter into site 1. So the number of particles that are entering the system minus the number of particles that are removed from the system up to time t. So this is the formal definition of this height profile. And yeah, when we will talk about the ASIP, we'll talk about this setup with the height function. Any questions about this system? Okay, so another piece of notation that we'll use. So first of all, OpenASIP is an irreducible continuous time Markov chain with finite state space. So it has a unique invariant measure, which we'll denote by pi with sub-index n, and tau, this variable which corresponds to the sites of the locations of particles. And we will denote the expectation with respect to the stationary measure by these brackets. So this is the notation. So now the question, we need overall we will connect the there's a connection between the height function of the open ASAP and the solution to the KPZ equation. So in order to understand the stationary measure for the KPZ equation in particular, we will need a very precise information about the stationary measure for the open ASAP. And again, here, what happens is that when you consider the open ASAP, so the presence of this reservoir makes life much more complicated. So similarly to the KPZ equation, ASAP can be considered on the whole line. So when you don't have the presence of these reservoirs, and then the stationary measure is simple and similar when the particles when you consider the periodic boundary conditions, when the ASAP on the ring, then also the stationary measure is simple, and in both cases it's the Bernoulli product measure. However, it's been known for quite a while that for these for the case of the presence of the reservoirs, the situation is much more complicated, and the precise description of the stationary measure has quite a complicated form. Okay, so I will. It's written in terms of the so-called matrix product ansatz. So this algebraic tool was initiated in the work by Derrida, Evans, Hakim, Pasquier, very fundamental and important work in this field. And then the following question was studied. So here we will talk about the phase diagram for the open ASAP at stationarity when n the number of particles, the number of sites, n goes to infinity. So the question is about, so this diagram is written in terms of the following object J, which is called the current. So the current is, so J here is the scaled. So first, let's consider finite n. So Jn is the ratio between the net current of particles and the ratio of net current of particles divided by t times 1 minus q. So at stationarity, the dependence on t on time disappears, and moreover, it has been shown that this quantity has a limit as n goes to infinity, which is denoted by j in this picture. And it was shown that depending on the parameters of the system, alpha, beta, gamma, delta, and q, this j, the current, can take only 3 values. So there are these 3 phases of this diagram, and J here is written in terms of 2 parameters, rho L and rho R, which physically represent the densities of particles at the left edge of the interval and the right edge of the system. So these parameters, rho L and rho R, they can be explicitly written in terms of the parameters of the system, alpha, beta, gamma, delta, q, but the formulas are quite complicated. So this is the diagram that was obtained. So it was obtained like in this form by Sandow. However, there were like some approximation that he used in his work and rigorously, and also with like with an introduction of a very important tool of the Askew-Wilson polynomials as the solution to the matrix product ansatz, which this phase diagram was proved in the work, in a seminal work in this field by Uchiyama, Sasamoto, and Vadati in 2003. Okay, so what do all these phases represent in terms of the system? So there are, the phases are called low density phase, high density, and maximal current. So physically, they mean the following. So in the maximal current phase, the left boundary creates particles at a fast enough rate and does not remove particles too quickly, so that the system is able to transport particles from left to right at its maximal efficiency. So the left boundary creates fast enough, and the right boundary does not remove them fast enough. So this is like this. This gives us the efficiency, and this is the maximal current phase. Now the low density phase is when the left boundary creates particles relatively slow, and the right boundary removes them fast. So this is so fast in such a way that they do not build up there. So this is the low density phase, and the high density phase is dual. So it's like vice versa. You need to change the right and left compared to the low density phase. So this is the physical meaning of all these three phases. However, so this is the phase diagram at stationarity and as n goes to infinity for the open ASAP. Okay, in particular, the following law of large numbers holds. So I will write it in terms of this occupancy variables. If we start at stationarity and consider this weighted sum of the occupancy variables tau j, then we'll see the following three profiles depending on the type of the phase that we are in. So it can be 1/2 times x if it's maximal current phase. So this is the law of large numbers for the open ASAP. Now I will explain how the connection between the open ASAP and the KPZ equation is made. So it's made through the consideration of the following weakly asymmetric scaling of the ASAP. So here we again have these parameters u and v, which are real, and we scale the parameters ρl and ρr near the value 1/2. So if we go back to the phase diagram, this scaling corresponds to zooming into this triple point on this diagram with respect to the following rate. So the second term here for ρl and ρr is 1/2 square root of n times v and u, depending on like whether we are on the left or right. Then we so in terms of the original parameters of the model, alpha, beta, gamma, and delta, it has the following form. So this scaling, if we take q to be the exponent of -2 square root of n, and write alpha, beta, gamma, and delta in the form of the following ratios. So this is the interpretation in terms of the original parameters. So now the connection is made between the following rescaled height function for this model at stationarity. So we need to scale the parameter. At stationarity, we drop the dependence on time. So we scale the space parameter linearly with n, and we also have 1 square root of n scaling in front. And this defines the object which is called H capital N of x, which will relate to the KPZ, to the open KPZ equation. The connection between the ASAP and KPZ equation and solution to the KPZ equation for with the weakly asymmetric through the weakly asymmetric scaling was first obtained in the case of the full line by very important work of Bertini and Giacomini, and then for the open ASAP by the work of Corwin and Shen, and in the case of the parameters u and v being non-negative, and in the case of for the full generality by Parech in 2019. Yeah, so this is the scaling that they use, and now I will present our main result with Ivan Corwin. So first of all, we show that this objects, capital H with label N. Yeah, so here we have the also a parameterization in terms of these boundary parameters U and V. We check that they fall into this setup, which were considered in the previous works, which I mentioned on the slide, on the previous slide. So we show that for the stationary initial condition, this sequence of HUV is tight, and we show that all subsequential limits under this scaling, they are stationary measures for the open KPZ equation, and moreover, we also obtain certain regularity properties and like other probabilistic properties of for this sequence. So we check that in particular, we check that the limits here are Kardar-1/2 almost surely. So this is the first part, that the limit indeed gives us the answer, the stationary measure for the open KPZ equation. And we also, like in many places in the proof, we need the following coupling property. Yeah, so we call these limits the WASEP stationary measures, so the stationary measures of the open ASEP, which come from this connection to the open ASEP. Yeah, so the other property that we show is the coupling. So this is this is very important technical property, which tells about the ordering. If we fix the order on the boundary condition, so this UIs and VIs, then we get the following inequality for the sequence HUV. So this is the property that we show, and most importantly, we obtain the characterization. So the first two results are for general case of U and V. So the last one, we need to assume that U plus V is positive. Then we show that this WASEP limit is unique. And moreover, we can characterize it uniquely. So it's determined uniquely by an explicit multi-point Laplace transform. So we get also this characterization of the limit. So this is the main result that we obtain. I want to show how this Laplace transform looks like. So in a special case, when both parameters U and V are positive, all formulas are much more simple. So here, like for the illustration, I assume that U and V is positive, and we also in this Laplace transform we need certain restrictions on the parameters of the Laplace transform. So this parameter C here is assumed to be in this interval. So then the expectation of the following exponent can be written in terms of the ratios of two integrals which involve a bunch of gamma functions. So indeed, like this description that we get, seems to be much more complicated than just the getting like something Brownian in the limit. So this expression does simplify in special case when U plus V is equal to 0, and it's indeed gonna give the Brownian answer, but in general, it's much more complicated. And this complicated behavior is related to a certain class of orthogonal polynomials, the dual Hahn polynomials, which I will talk about next. And like in general, this like all this computation are very much related to the like one of the topics of the program about the asymptotics of orthogonal polynomials. Okay, so this is how it looks like. And yeah, I need to make a couple of the remarks. So first of all, we show the uniqueness of this weight measure, but still it doesn't show the uniqueness of the stationary measure for the open KPZ. So in the case of the full line and periodic boundary condition, the uniqueness was established in the same works that I cited. However, like in our work, we do give the representation for this particular stationary measure, which comes from ASAP, but we do not show the uniqueness, which is expected. So the uniqueness is conjectured in this in the case of the open KPZ equation as well. So this is like one of the important future directions of this work in order to understand the steady state of the KPZ equation. Another natural question is about the probabilistic description. So we get this characterization of the WASEP stationary measure in terms of the multi-point Laplace transform. However, it would be much nicer to have a description like a more probabilistic description of this object. So to invert this Laplace transform, and indeed. It turned out to be possible. So we posted our work on arXiv in April, and in May, and two other works appeared in physics and math literature, which essentially invert the Laplace transform that we obtain for certain range of parameters U and V, and give a nice probabilistic description of this process that we obtained. I will talk about it briefly on the next slide. And the third question, which is also natural, is the question about the generalization of our work to half space. So another type of initial condition that people consider is the half line. So instead of having two reservoirs, we have just one reservoir on the left, and then like particles can, and then like in terms of ASAP, particles can jump on the integer sides on all positive integer sides, or in terms of the KPZ equation, we consider the interval from 0 to infinity. So this is the KPZ equation on the half space, and from our arguments, so we work on the interval from 0 to 1. We can extend our arguments to be valid for any interval from, say, 0 to capital M. And then the question is how to rigorously pass to the limit as M goes to infinity in order to obtain the results which are mathematically not known yet for the stationary measure of the KPZ equation on the half space. So yeah, we also believe that it's possible to be done like based on the computations that we already have available. So this are a couple of future directions which I wanted to mention. And now about this probabilistic description, which recently appeared in the following works. So it first appeared in the mathematical on the mathematical side, in the work by Brick, Kuznetsov, Wang, and Vasilovsky, and then in physics literature for a general class of parameters U and V. So not just like for U plus V greater than 0. So they do the computation of the inversion for the Laplace transform that we obtain, and also they have the prediction what it should be for the whole range of parameters. So it's been done like around 10 days ago by so it appeared about 10 days ago by Barkhan and Le Dussal. And the description is the following. So if we look at this limit stationary measure HUV, it's equal in law to the following sum of independent processes. So the process B, the Brownian motion scaled. So we have this scaling 1 over square root of 2 plus process X, where process X. So this particular description is taken from the physics paper, but it's equivalent to what is obtained in the mathematical one. Yeah, so this process X is independent of B, and it absolutely continuous with respect to the Brownian motion with diffusion coefficient 1/2. So here it means the variance 1/2. And Berkan and Ledusal, they give the explicit formula for the Radon-Nikodym derivative of the process X, so it determines it uniquely. Yeah, so this is the probabilistic description of the answer that we obtain. So this process X, the definition of the process X, it involves the parameters U and V. So that's where the boundary condition is hidden in this formula. Yeah, so still personally, I think there's quite a bit to be understood here, like about the nature of, like, even though it's written explicitly, there's quite a bit of information here which is still not understood like very well about the nature of the appearance of this process X in this context. Okay, so this is the probabilistic description of the result that we get. So now I want to explain like the main ingredients that we use in order to obtain the characterization. So the main ingredients in the part about the computation of the Laplace transform in our work. So we start with the description of the stationary measure for the symmetric simple exclusion process in terms of the matrix product, matrix product ansatz, which was initiated by in this work by Derrida, Evans, Hakim, Pasquier, and then we use this connection that was introduced. This very important connection, which was introduced by Chiam Samoto-Wadati with the Askew-Wilson to the Askew-Wilson polynomials. And well, the particular form of the result that we use is due to Brick and Veselovsky from 2017. So they show that in the region, in the so-called Fend region, so in our notation, it's when it's exactly when U plus V is greater than 0, the following formula is valid. So the joint generating function of the station distribution of the ASAP is given in terms of the ratios of two expectations according to the process YT, which is the so-called Askew-Wilson process, which was also introduced by Brick and Veselovsky in their previous work. So this particular form of the connection between the stationary measure for the ASAP and Askew-Wilson polynomials is very useful for the asymptotic analysis. So there are like other, as I mentioned, there are other connections. And in particular, I should mention here the like the beautiful connection to the combinatorics of Tableau, which is which was obtained by Cortil and Williams. However, in our work, like this particular formula by Brick and Veselovsky, it turned out to be the most useful for the asymptotic analysis. And here this process, the Askew-Wilson process, is a Markov process whose marginal and transitional distributions are written in terms of the weight function for the classical orthogonal Askew-Wilson polynomials. So here I'll show the definition in the for this process for the special range of the time parameter t. So in general, This measures, the marginal transition probability measures, they are not continuous. They also involve atomic parts, and that complicates the analysis by quite a bit. So in our paper, we work with this much more general. So we will need to consider more general cases with these atomic parts. However, for a special range of the time parameter at C, the marginal pi can be written in this form, where so I was talking about the definition of this Askey-Wilson process in terms of the orthogonality, like this weight function for the Askey-Wilson polynomial. So this product of Q-Page-Gamma symbols. So in particular, when we work with the asymptotics of this process, with respect to this weakly asymmetric scaling, one of the key asymptotic ingredients is the understanding of the expansions of Q-Page-Gamma symbols when Q goes to 1. So we do the following analysis. We look at so let Q be e to the minus kappa, where kappa is the parameter, which will be small. And we look at the logarithm of the Q-Page-Gamma symbol. And we want to look at the expansion of this as kappa, for kappa very small. And the particular difficulty here is to have a very good control over the arrow term simultaneously in Z and in kappa. So this type of question, the expansions of this sort were studied before in the literature, in particular in the number theory literature. However, to the best of our knowledge, this question about the balance between the parameters Z and kappa were not addressed before. Yes, and it's like precisely the type of the control that we need for our results. So this is like one of the key ingredients for the asymptotic analysis that we use. And so this part was, this part relies on a number of standard tricks and like methods from the analytic number theory. And it was a lot of fun to study all of these things. Okay, so this is the one of the key technical parts. And in the end, I want to make this connection with the another class of orthogonal polynomials, the dual Hunt polynomials. So with the so overall, I've showed how the multi-point Laplace transform looks like for the very special case of the parameters U and V. It turns out that it can be written in a quite nice form for like this general case of parameters U plus V greater than 0 in terms of another process which is related to dual Hunt polynomials. So again, here we for simplicity for this talk, we assume that parameters U and V are positive. We restrict ourselves to a certain interval of time. So now time is S, where this capital C UV like has this form depending on parameter U. And then we define the marginal distribution for this process, again, in terms of the gamma functions in this way. And the transition probabilities which appear in the bottom of the slide, PST, are written in terms of function CDH, which is the weight function for the dual continuous polynomials. So again, we need to make sense of all of these functions. We need to have certain restrictions on the parameters on this time parameter S and T. So they are in this interval. And again, U and V here I assume to be positive. In general case, when U plus V is positive, all these measures, they also involve atomic parts, so the formulas are much more complicated. And the final result that we obtained as the characterization of the limit stationary measure for the open KPZ equation can be written in terms of this the process, which are defined through the dual Han through the orthogonal measure for the dual Han polynomials, as presented before, in the following way. So the expectation of this observable, the exponent of minus linear combination of HUV at locations xk can be written as the ratio of expectations with respect to this process, which we call dual Han process. So it was quite unexpected for us to see like this, like the appearance of this particular orthogonal polynomials in the limit, and yeah, like also we were happy to obtain this a nice description for the Laplace transform in terms of these expectations with respect to this process. So this is the final result about the characterization. And yeah, I will stop here. Thank you very much for your attention. Yeah,
Thank you.
Yeah, I am sorry for having some
David,
connection.
Can I ask a question?
Yes, yes.
Well, first of all, Alisa, thank you very much for this extremely up-to-date presentation on KPZ. I mean, I appreciate a little bit about the pressure that younger people are under when they have to incorporate into their talks at the last minute things that only appeared on the internet 10 days ago. I want to make a comment historically. There was a name that's very important to me. It was never mentioned in the last hour, and that is Giorgio Parisi. Of course, you mention him all the time in the P and Z, but Mehran Kardar and Giorgio Parisi and Yichang Zhang 35 years ago made this great contribution to your subject, but Giorgio spans 3 of those: stochastic partial differential equations, statistical mechanics, and migrator's love quantum field theory. I mean, of all of my contemporaries, Giorgio is slightly younger than me. I think he has been deeply influential. And I've been listening to your talk all the time, and every time you said KPZ, I thought who the P was. Sorry for this personal comment, but yours is a suitable tribute to the influence that Giorgio has had on our subject.
Are there any other questions or comments? If not, that concludes the scientific part of the workshop today. I thank Alisa for her nice talk, and we'll resume again at 11 tomorrow morning.
Thank you.
Thank you.